Okay, look at this is, I'll show you in today's class how to write characteristic equation for the flip-flops that we have discussed in the previous class. Okay, what do you mean by characteristic equation? We can't call this one as a Boolean equation. We should call this equations related to the flip-flop as a characteristic equation, because this describes the characteristics, property of a flip-flop. I'll just go through them, and also keep in mind that we have discussed the following flip-flops. Latches we have discussed already. Okay, we have discussed SR latch, S bar R bar latch. Then we discussed gated D flip-flop, followed with SR flip-flop, then JK flip-flop. All those things we have discussed. When it comes to the pulse triggered flip-flop, we discussed two types of flip-flop in the previous class. Number one is master slave SR flip-flop, and other one is master slave JK flip-flop. There's only minor difference between these two flip-flops. Okay, I hope by this time you are aware of a difference between latch and a flip-flop. This is commonly asked question in many campus interviews. Main difference between latch and a flip-flop. Okay, latch is more or less, it looks like a combinational logic circuit, and latch doesn't have any control. It doesn't have any clock. Understand here? Just if you give input, the output will be changed after some propagation delay. That's only difference what you observe in the latch. And latch are even prone to noise also. Many times when noise comes as input, latch cannot make distinction between the input data and the useful data. Okay, that's the one difference what you can see in the latch. Okay, when it comes to pulse triggered, we already seen that the on pulse will trigger master flip-flop, and the off pulse will trigger the slave flip-flop. This we have discussed in the previous class. That's why it's called pulse triggered. And we have not discussed anything related to edge triggered, but pulse triggered and edge triggered, more or less it is same. Okay, there's no main difference. Only thing is here edge will change the output of the flip-flop, whereas in case of pulse triggered, pulse will change the flip-flop. On pulse will change one state, one part of the flip-flop. Off pulse will change another part of the flip-flop. So next, edge triggered is not there in our syllabus. I would suggest even to go through this edge triggered flip-flop before we move to the next one for the examination point of view. Okay. I've given main difference here, which you can go through here. Latches, it's the first class of flip-flops. Output responds immediately at all times. Okay, when it is enabled. Otherwise, no. Pulse triggered flip-flop, this is used in master-slave structure. Information enters master on first edge of the control signal, I mean clock signal, and second edge of the trigger pulse. The content of the master is transferred to the slave. Okay, so that's what we have seen in the previous classes. Outputs are postponed until the end of the triggered pulse period. Okay, we have shown the symbolic representation, and output will be postponed till the end of the clock pulse. You don't see any output. Entire clock pulse you have to wait to see the output in master slave JK flip-flop or SR flip-flop, whatever it may be. And edge triggered flip-flop, there is only minor difference between these two. The edges will change the state in the edge triggered flip-flop, whereas here the pulse will change the state of the flip-flop. Apart from that, there is no difference between the pulse triggered and edge triggered flip-flop. And before I move to the next one, let us see the characteristic equation. I already told you what do you mean by characteristic equation. I think I have a couple of points to discuss related to characteristic equation. This is a definition of characteristic equation. What do you mean by characteristic equation? It is an algebraic description of the next state, stable of a flip-flop. Is called characteristic equation of the flip-flop. As I told you, it describes the property of a flip-flop, nothing else. Okay, now we'll see how to describe the flip-flop with the help of a characteristic equation. The description is easily obtained by constructing K-map. You can use K-map, but of course, if you simply analyze truth table of any flip-flop, you can also write characteristic equation. But I would suggest to have a correct expression, use K-map. I will show you for all the flip-flop outright characteristic equation. And if you remember the characteristic equation, it's simply you can implement or you can realize them using logic gates. That's simply it's possible. And look at here, this is the characteristic equation of the SR flip-flop. Q plus, which is equal to next state, which is S plus R bar Q. How to derive this, we'll show that very soon. This is the characteristic equation of SR flip-flop. Okay, you can see here the next state depends on the present state, and there's a complementary in the R bar, and it also depends on the S. We'll see soon how to write, develop this characteristic equation for the SR flip flop and other flip flops as well. Any questions about definition? There's a lot of difference between the truth table, normal equation, and characteristic equation. In order to develop characteristic equation, you should develop what is called as the table, state table, and based on that you can write the characteristic equation. What is state table? I will just describe by taking an example. But previous to that, you can see that state table will contain present input and also present state. Those are the two inputs you will have in the state table, and based on that you produce the next state. If I take an example, you will understand what do we mean by yeah. This is what could you see this one? Can you see this? Okay, this is called as state table. As you can see here, what you have done in this state table. Normally in our truth table, what you have seen. Suppose it's an SR flip flop. Only you have seen 4 rows, right? Okay, S and R can be 0, 0, 0, 1, 1, 0, 1, 1. Now you see here we have broken that into the 8 states. How that is done? You can see here. 0, 0 I have split it into 2. This is 0, 1, 1, 0, 2, 1, 1, 2. That means I have divided each state into the two possible substates. And you can see for 0, 0, S is equal to 0, R is equal to 0. I have taken 2 combinations here. The present state can be 0 and 1. Understand this thing? And similarly for S and R, these are the present inputs, this is the present state, and this is going to be the next state. A table developed between the present input, present state, and connecting that to the next state is called as state table. This is very important table. Why I'm saying important is because based on this, although we develop a characteristic equation, but also used in counter design. If you want to become familiar with counter design, one must learn how to design, how to write the state table. This is called state table. Okay. Any questions about this state table definition before we go to the writing K-map, using K-map and deriving characteristic equation for that? All of you understood this? There's a lot of difference between the truth table and the state table. Truth table, what it tells you, only input and next states. That's what truth table tells. But look at here, along with inputs, what we have is S and R, the input of a SR flip flop. We also have what is called the present state. That means given the present state and input, we can decide what is the next state. That's what it's called as a state table. Okay? And based on this, we can develop a characteristic equation. Just look at here. Can we expand this first one, how it works? 0, 0. Present state is 0. The next state is going to be 0. According to our truth table, what is the output or next state for 0, 0 input for SR flip flop? Just look at whatever you have taken in the previous class. For 0, 0, there is no change, right? Next state will be no change state. That means whatever the previous state we have, that should be returned in the next state. I would do the same thing. Look at here. If 0, 0 is the input, if present state is 0, next state is also going to be 0. Same input, 0, 0, but present state is 1. The next state is also going to be 1. That means I've just copied this to here, that's all, nothing after it. Can we call that as Q plus is equal to Q simply? That's what we have done in the truth table. Understand here? The Q plus will be equal to what? Q. Exactly we copied here. Hope you understood the first 2 rows. Okay, let's move to the next 2 rows. I've changed input here and also state has been changed into 0 and 1. Look at here 0, 1, 0, 1. So this 1 is not visible here. I would like to make a note of this. Suggest you to make a note of this. And look at here what happens for the truth table in case of SR flip flop for 0, 1 input. It will be 0 only output, right? And also here I have not showed here complement of Q plus here. Are you seeing here, observing here? It's not required, it's implicit. I did not show every time the Q plus bar here. I only showed here the Q plus. Understand here? It's implicit that there is even Q plus bar exists. Don't think that intentionally I have removed one more row in the output. Q plus bar is not shown because it's understood that it is there. Okay? Only Q plus we have shown in the output column here. Okay? So let me move on to this. For 0, 1 input and 0 is the present state, the output will be the 0. Okay, same thing happens for 0, 1 input. When the present state is going to be 1, the next state will be still 0 only. Just look at truth table. Based on that, you can easily write the state table. Understood this? Any questions? Now you can also interpret what will happen when the input changes to 1, 0 with present state as 0 and 1. Input changes to 1 and 0. Look at here 1, 0, 1, 0. Present state changes to 0 and 1. What happens now? You can see that. Our next state is going to be the 1 and 1 only, irrespective of the present state. You can see here, this is 1, 0. Irrespective of the present state, output changes to 1. Got it? Okay, last one you can see it is forbidden state in case of SR flip-flop. Last state. Last state is input S is equal to 1, R is equal to 1. Present state is 0. Same way, input 1, 1, present state is 1. I have taken two combinations of present state. What is present state? It is what you are assuming, right? Before you switch on the SR flip-flop, give power to the SR flip-flop, input data, present state, at output you are observing this. This is going to be the present state 0. When input you applied is 1 and 1, next state is going to be undefined state. What is undefined state? Both going to 1. That's called undefined state. We don't expect this. This is called forbidden state. And we treat that as don't care in the K-map representation, because I told you that we use K-map for deriving the characteristic equation, what you are saying here. This is a characteristic equation. You can also, just by analyzing the state table, you can obtain this characteristic equation. But I would suggest to have an accurate expression, I would suggest to use K-map. K-map is the best way to simplify, obtain the reduced form of equations. Okay, I suggest always use K-map. K-map is a powerful technique, especially for less number of variables. When more number of variables, we already seen that there's a Quinn-McCluskey method, variable entered mapping methods, so many reduction methods we have. Understood these things? Any questions about this? These inputs are not allowed. We take them as don't care in the K-map. Okay, we use for the pairing purpose. We take them as a don't care. Now we can see here. This is what the K-map representation, the state table. What we have here, we have converted that, we represented that on the K-map. K-map here is slightly different technique what we follow compared to the module 1 what we have discussed. In module 1, you can see that we started with this is our MSB, this is our LSB, right? In the very first module 1, what we are told is just a reverse in the K-map representation. You can see an MSB comes out the top and LSB comes out at the bottom. Okay, this is very important in writing the number, giving numbers to the square. If you just confuse here, you will go wrong. You follow any one method. I have followed here this method because for the module 3, reason is we are following different textbook, right? Textbook to textbook, there is a change in the MSB and LSB representation. In module 1, we followed the Erubro textbook. In that, the LSB used to be at the top and the MSB used to be at the bottom, below the diagonal line. But look at in this, given in textbook, we follow MSB should be at the top and LSB should be at the bottom. Better to write down somewhere so that you don't forget. Whenever you are in module 3, this notation has to be followed. MSB at the top of the diagonal and below will be the LSB. This is our LSB. Q is LSB. Look at here. Q is LSB. Whatever comes to the rightmost side is LSB. And S is going to be the MSB. So MSB is above diagonal line. S and R, these are the inputs. Q is the output. Q is the present state, not output. Understood this? The moment you know this, then other things it's evident from the K-map. How do you represent K-map? 0, 0, 0, 1, 1, 1, 1, 0. You must write, since the two variables are there above, the diagonal, okay, I have written all possible combinations such that there must be only one variable change. From 0, 0 to 0, 1, you can see the column wise of K-map, there is one variable change. I can't write here 1, 0. If I write here 1, 0, there will be two variable change. So therefore, I have written here 1, 1 here. From here to here, you can observe here 0 changed to 1, 1 remained as 1 only. That means there is one variable change. And look at from here to here, there is again one variable change. That concept you have followed here, even here also. And if there is only one variable, there can be two combinations. That means this K-map is 2 row and 4 column K-map because of 3 variables. Any questions here? All of you followed this? And we are developing characteristic equation for all the flip-flops, starting from SR flip-flop to JK, D and T flip-flop. This is another way of representation of a flip-flop. Understand here? How do you represent a flip-flop? How do you describe the working of a flip-flop? Theoretically, you can write some paragraph and explain the working of a flip-flop, right? That's one way. Many times we tend to forget most of the things while describing the flip-flop. But the other way, to explain the working of the flip-flop, go through the truth table. You have to understand the truth table and explain that truth table. That's another way. Third way is you can write even characteristic equation like this for the flip-flop, and from this also you can describe the working of the flip-flop. This shows that simple few gates are required, right? You can have NOT gate, AND gate, and OR gate. If you have simply these things, you can even develop a flip-flop. Okay, let's right now represent this table onto the K-map. I've given you a serial number, you can see here 0 to 7. Because to make it double representation easy, and K-map here follows 0, 1, 2, 3, 4, 5, 6, 7. Understand column wise. Because I told you, because when you change the LSB and MSB, it will shift to column or row. Understand here? How I know that? How do I know that? It's very simple. Look at here, this is going to be our MSB, right? S and R. Read from here 0, 0, 0. This cell is what? 0th cell. Understand here? This is our LSB, remember that. Q is our LSB. MSB 0, 0, right now somewhere 0, 0, 0 corresponds to 0. What about this one? 0, 1, 0 corresponds to what? 2. Understand here? You must know how to number the squares. Look at here. 1, 1, 0. 1, 1, 0 is equal to what? 6. Understand here? Even without going in order, you can also write randomly the number in each and every cell. This cell numbering is required to map this K-map outputs to this. Now what I've done, it is this Q plus represented on the K-map. You can see here 1, 4, 5 are 1. Look at here 1, 4, 5. And even this got don't case. I've taken a represented on K-map. Remaining are going to be 0. 0 cell is 0, 2 is 0, 3 is 0. All are 0. Remaining are 0. Once you represent this state table onto the K-map, then only the grouping must be done. Grouping is very simple. One will map with, one can be paired with 5, and these 4 cells can be grouped together. You can see here 4, 5, this is 2 and 6, not 2, it is 6 and 7. This can be grouped as a quad, and you can get simplified equation. This gives you the single variable which is S. And this pairs, this cell number 1 and 5 gives you the variable as R bar Q. You can look at here, from 1 and 5, this Q remains same constant, this is row wise, and column wise if you see 0 and 1, S cancels, and you're left out with R bar. Therefore it is R bar Q. Okay, so that's how you can write the equation from the K-map. So finally, this if you look at this quad wise, you can see here, this both Q will cancel because it is mapping to both the rows. And look at column wise, 1 and the first one is retained, and second one will get cancelled because of 1 and 0 here. First one variable is S, so it is only simply S. Okay, so the final equation is S plus R bar. That is the equation. Okay, similarly you can also write the state table for the JK flip-flop and obtain the characteristic equation for the JK flip-flop. Just go through that. If you have any questions, you can ask me. The same procedure what I showed for SR flip-flop, I followed for JK, D and T flip-flop. Okay, this is another way of describing flip-flop with the help of characteristic equation. Okay, any questions are there? All of you understood SR flip-flop? Look at JK flip-flop, only difference is here. Rest all SR flip-flop and JK flip-flop both are same. Are you observing here? From cell number 0 to cell number 5, you can see everything is same, no change. But only difference is last 2 rows. Look at what happens in J and K when both are 1, 1. Toggling should happen, right? So 0 is the present state, next state will be 1. That means 0 is changing to 1. That is flip-flop is toggling. And when the same input is retained J and K, when the present state is 1, toggle state means the state should change from 1 to 0. The last 2 rows are different. Rest all the SR flip-flop and JK flip-flop working remains same. Understand here? That means from here to here, we have avoided the undefined state or forbidden state. That's only change in the JK flip-flop. Next step is, once you write this state table, remember this is not a truth table, this is state table. Because here we have inputs and state, present state, followed by the output. Okay, this is called state table. Now represent this state table on the K map. This is a three variable, the K map I used here because three variables are J, K and Q. J and K are the inputs, Q is the present state. That's why this J, K are taken as inputs here, J, K, Q, present state. And you can write Q plus output by representing this column on the K map. And everything remains same as we have shown here. 1 and 5 remains 1 and 6 and 1. But here you can't map with this 0 because earlier this was a don't care, right? You have treated this as a don't care. But now it is no more don't care here. You have zeros and ones. Only two combinations exist in the entire K map. Either you can find 0 or 1 you can find. So these 6 and 4 can be grouped. 1 and 5 can be grouped. That gives you the two terms here. J Q bar. J Q bar you can get it from this one. Q bar is common. From this you will get it as J. And from the for cell number 1 and cell number 5, you will get K Q bar. K bar Q. You can see here. Okay, because Q is common here, and from the first cell and fifth cell, you will get just K bar. Okay, so the final equation for this is Q plus next state is now J Q bar plus K bar Q. Okay, this is the characteristic equation for JK flip flop. Okay, now without saying, can you develop for D and T? Okay, just we have showed for SR and JK. Can you write the state table without looking at the board? Can you write it for D and T flip flop? Just go ahead. Let me see that how many of you can do that. Right. First write for D flip flop, then we can go for T flip flop. First write the truth table of D flip flop, then you can write state table for the D flip flop. Write truth table for D flip flop. You have only 2 rows, right? But you have to make it here 4 rows. Why is 4? In state table. You have to know along with D there will be Q also, right? Just like here, see, this is all 4-row truth table. How we make it as 8 rows? By duplicating the input, right? Because there's present state as 0, present state also will be the 1, right? I would suggest to write table first for the D flip flop. Ignore the clock here. No need to show clock on the truth table. Just write the D, and along with that you can write Q plus. What will be the output for this? If it is 0, it is 0 only. If it is 1, it is 1 only. Now this truth table, this is the truth table. You have to make it as a state table. How do you make it as a state table? Along with the D, you should also have what? Q, and you will also have Q plus. This is what the state table, right? Okay. Now you can get here, there are 2 inputs now. You will have how many combinations? 4 combinations. D and Q will have 0, 0, 0, 1, 1, 0, 1 and 1. As I told you, clock is implicit here. You did not show clock pulse. Okay, for every row here. Now can you write based on this now? Look at the truth table now. For 0 input, 0 is the present state. What will be the next state? 0. 0 input, 1 is the present state. 1. 0. This is where the confusions will start. 0 or 1? 1. 0. But data flip flop, right? Whatever the input you apply, irrespective of the present state, it goes to the D input only. What is the equation? Q plus is equal to D, right? Okay. All of you understood? It's not irrespective of present state. Let's not bother about present state. Present state can be 0. Present state can be 1. Understand here? Whatever D flip flop will do, exactly whatever input you apply, it will transfer to the output. So input what you applied is 0. It's straight away transferred to the output irrespective of whatever the present state. What about here now? There's something similar you can write. 1 and 1. That's see how simple it is. Now next step is represent this on the K map. Now how many cell K map you will use here? You can't blindly go for 8 cell K map. But go for 4 cell K map and your equation will be very simple. Just go ahead and do that. Feeling difficult, you can see that D flip-flop, the state table I've shown, K map also I've shown that. First one. Upper here you can see the truth, this is the state table. 0 0 0 1 1 0 1 1. Same thing what I've written on the board. Q plus will be 0 0 irrespective of the present state. And look at here, it has been 1 1 irrespective of the present state. Now for that, K map now consists of just 4 cells. Okay, and you can look at the variables here. Q and D are the variables. D is MSB, which is above diagonal. Q is LSB, below diagonal. Okay. So 0, 1, 2, 3. There's the cell numbers. Column wise I'm showing here. Since it's not visible here, this is first cell is going to be 0th cell, first cell, 2 and 3. Just represent on this 1 1. You will get Q is equal to D. Straightforward here. Nothing difficult here, right? This gives you, just if you group here, that gives you Q plus is equal to D. Is it clear to all of you? Just if you remember the equation, it is sufficient to understand the flip-flop. Okay. Next, move on to the toggle flip-flop, T flip-flop. Look at how T flip-flop works. That is explained through the state table also. Okay. T flip-flop, you can see here. For 0 input, present state is 0. What will happen to the next state? What will happen to the next state? Just tell me the truth table of T flip-flop. For 0, there is no change. For 1, flip-flop will what it will do? It will toggle. Understand? For 0, Q plus will be equal to what? Q. Q plus will be equal to Q. A small change in the here. Instead of having here, it remains same. For 0, it is Q. For 1, it is. Understood? This is a truth table. Based on that, you can write state table like this. See, we have not discussed more details of this T flip-flop, but here to write characteristic equation, I'm using here the truth table of T flip-flop. Look at here, 0 input, T input is 0, present state is 0. According to truth table, what will happen? If 0 input is applied, no change, right? No change means 0 should be continued with 0 only. Okay? And look at here, for 0 input, 1 is the present state, 1 will be continued. The next state will be equal to 1 only. Clear? And look at what, when the T flip-flop will toggle. When there is a 1 input on T, remember all this, whatever I am saying, next state will change only on applying the clock pulse. Understand here? There is no magic here to change immediately. They are not combinational circuits. They are all sequential circuit. It has got memory. Okay. Only when the clock pulse comes, if it is a pulse triggered, when the on pulse comes, then only flip-flop is going to change its state. Though you might have applied here 1, present state may be 0. For the next state to change here, clock pulse should be applied. Understand here? Either level triggered or edge triggered clock pulse must be applied. I'm assuming that here clock pulse is applied, then only when the T is 1, you maintain T input as 1, 0 will be now toggled to 1. 0 changes to 1. If the T input is 1, if the present state is 1, before you turn on, before you apply the clock pulse, I should not say turn on, I should say before clock pulse. Before clock pulse, if it is 1, after clock pulse it will change to 0. Provided if the input is what? 1. You should not change the input. Understand here? That's how the T flip-flop works, and this is the characteristic equation for the T flip-flop. How do you develop that? Again, it is a 4-variable truth table. It looks like a truth table, although it is a state table here. Represent this on the K map. You will see this here 1 year, 1 year. You can't pair with anything. Understood? Any questions about T flip-flop before we move on to the registers? I hope you understood, all of you, how to write, develop characteristic equation for every flip-flop. Okay, with that we will move on to the next topic, which is registers. And there are a lot of problems, exercise problems from the textbook. Understand? I suggest you to go through the textbook and solve, as many problems as possible. Don't stick to the just examples, work examples, problems what I solved here. I would suggest to go to the exercise problems, and I think I would done this. Sorry. Yeah. I suggest you to go solve the exercise problem. This is actually one of the exercise problem given in the textbook. Even though they showed for SR flip-flop and JK flip-flop, they asked you to develop for D and T flip-flop. I thought let me extend that and solve even for D and T flip-flop. It's very easy, see, it's not so difficult, right? Okay, let me move on to the register. What is register now? After this, we'll go on to the counters. Okay, these topics are not difficult. I'm suggesting you this is very simple. Only thing is, if you understand, it becomes easier. If you don't understand, it becomes very difficult. Don't try to buy anything and produce in the examination. Understand? Try to understand concepts and don't write more theory also. This is not a theoretical subject. This is logic oriented subject. You must write logic very well to score more marks in the examination. Don't write page wise. Even ask you about, say, write characteristic equation. There is no need to write theory behind the characteristic equation. Just definition, and what is required is the truth table, then state table, then K-map, then the equation. Do step by step. Organize your answers step by step. Most of the times you lose marks because you try to do over explanation sometimes beyond the limit. Don't do that. What I suggest you is always be limited. It's a logic oriented subject. Alright, let me move on to the registers. We have discussed simple applications so far. I hope by this time you must be aware of flip-flops. That's the first thing. Don't make noise, those who are sitting back. Okay. We have discussed so far what it is, whatever we have discussed, I'm just making it, we have discussed just flip-flop. This topic expects you to be familiar with the flip-flops. Without studying flip-flops, you can't move to the registers. In simple word, I can say register is a group of flip-flops, right? Okay. Any other definitions you have apart from this? Register means you club several flip-flops together, you can make a register. Register is something different. It is a memory actually. Understand here? If you want to build a very big memory, you can also have many such registers. One register will store at least 4-bit data, 8-bit data, or sometimes 16-bit data, 32-bit data. We're just explaining you how to store one number, a binary number. Binary number is made up of multi-bits, right? There can be binary number with 2 bits also. There can be binary number with 1024 bits also. If I ask you to develop a shift register to store 1024 bits, you are supposed to construct flip-flops, group together 1024 flip-flops. One flip-flop can store 1-bit data. 1024 flip-flops can store 1024 bit data. And I will tell you the very simple thing in VLSI design or chip design is, if you want to realize them in the hardware or develop IC of your own, it's very simple to duplicate here. Understand here? But in hardware lab, it is quite difficult. In hardware lab, if I ask you to develop, say, 1024-bit register, you have to struggle whole day and try to make connections and see whether you are able to store or not. It's very difficult. Practically, I will tell you it's highly impossible. You'll go mad by the end of the day by developing 1024-bit. First of all, do you have 1024 flip-flops in the laboratory? That itself is a very big question mark. Okay, then where's the question of developing 1024-bit register? Maximum we can have, at least 100, not more than that in any laboratory. But look at here in the hardware design, if you want to simulate this, it's quite easy. Write one piece of code and duplicate, 1,000 times. Probably one of the complex design, I spent almost 6 months to design about, 1 million flip-flops. Every day I used to code, 1 flip-flops and copy them, copy-paste. Okay, it's very tricky kind of things, but you can do duplicating also. It's very intelligently you should do it. Otherwise, if something goes wrong, everything will collapse. Hardware design will collapse. Okay? Hardware design will take a lot of time. Okay. So the just sequential networks. I just want to tell you the difference between sequential networks and combination network. Though we have told already definition. Sequential network has memory, and this can be achieved through the flip-flops. Memory means flip-flop should be there. One flip-flop will store 1 bit data and capable of storing zeros or ones. I'm just extracting the content from the textbook straight away. I made it a little bit easier for you to, instead of studying the entire book, what I suggest you is, from this you can prepare your own notes and study from that. Or else you can follow straight away the material what I'm going to share with you. It's simple. So, flip-flop is capable of storing 0 or 1. It corresponds to binary digits or logic network. These are called sequential networks. Sequential network has got memory. It can store. Memory is achieved through the flip-flops, and flip-flop can store 0 or 1. That's nothing but binary digit. And register simply it's a collection of flip-flops, nothing else. You group several flip-flops together, and that is called as flip-flops. Register holds information within the digital system. And you may ask a question where this is used. There are many applications of registers. If you want to move the data, I myself used, in plenty of applications, let me tell you. When you want to convert serial data into the parallel data into the serial data into the serial data, and when you want to move the data from one flip-flop to the next flip-flop, which we call as shift registers. In various applications, we keep using shift registers, general registers. I hope you understood the definition of what we mean by register. Register is nothing but it's a collection of flip-flops, and use flip-flops to store data, memory. And this is the summary of this is the topic connected with the previous characteristic equation. Just if you are not aware, please go through this truth table. This is again straight away, randomly I arranged the slides here. Yeah, continuation is here now. Register has got additional capabilities also. As I told you, register can be used to move the data from one part of the flip-flop to another part of the flip-flop, another flip-flop. That is called as a shift register. This is a definition for shift register. The registers that are capable of moving information position-wise upon the occurrence of the clock signal. That is called shift register. First we defined what is register. Next I am defining what is shift register. Shift register can move data position-wise from one flip-flop to the next flip-flop, from one memory element to the next memory element. This movement will happen smoothly upon the occurrence of the clock signal. Without clock, nothing will happen. Clock is like a heart pulse for the flip-flop and shift registers. When you apply a clock, things will change. Otherwise, it will not change. So clock is mainly the controlling element in all this flip-flops and shift registers. And coming to the classification of the shift register can be classified as, look at here on what basis it has been classified. The basis here is on data moving direction. And which direction the data moves. Upon that we can classify it to unidirectional, bidirectional. I did not expand this, what is unidirectional. It moves only in one side. You can move either to the right side or you can move data to the left side. That is called only one particular direction you can move the data. Such registers are called as unidirectional shift registers. Bidirectional, I will show you one or two examples. I think in the textbook they have come out with one example of unidirectional shift register and bidirectional shift register. And if you see bidirectional shift register, complexity will increase because in both the directions you can move the data. Either right side or left side you can move the shift the data. And of course, the complexity increases because you want to provide additional signals like direction. Also, you should provide. User should know which direction is moving the data. Understand? And also, we give additional possibilities. We'll show how what are the possibilities we have in the bidirectional shift registers. Another way of classification is serial shift register, parallel shift register. What do you mean by serial shift register? The word serial means one after another. Understand here? Suppose I have 4-bit data, I want to shift one after another from the left side to the right side. That I can do using serial shift register. Parallel. At a time you can apply parallel data. Suppose if binary number is 1011, completely I can load with the shift register. That's called parallel shift register. This is another way of classification. And this classification is based on the manner the information is entered and outputted. Based on this, we can categorize shift register into the two types. And again, the 4 more ways to classify the shift registers. Okay, that can transfer information. It can be serial in, serial out, serial in, parallel out, parallel in, parallel out, parallel in, serial out. These are the 4 possibilities we can have data movement within the shift register. I will tell you that these all things what we are learning may not come into use right now, but when you develop any system and some other occasion, you may have to develop these kind of things. At that time, you will forget all these basics. But you should keep in mind that data can be moved either from taking serially and it can move parallelly also. All these possibilities are, all these things are possible in the shift registers. Okay? And don't think that every time we go for IC based shift registers, we normally model this using the tools. Tool modeling is very simple compared to the practically constructing these circuits. Okay, I'll show you how to do that in the module 4. How to use a tool-based technique to model all these kind of the sequential networks. Let's have one example. Look at this example. This example, if you look at here, what is this example is now? Serial in, serial out, unidirectional shift register. What do you mean by that? One direction, this moves data in one direction. Which direction it is moving now? Here a serial data input, and there's a clock here, and you can see a clock is common for all the flip-flops. Just for example's sake, I've used here 4 flip-flops here. That means I'm storing 4-bit data inside this, and I'm moving that to the right side, okay, a bit by bit. Because look at here, serial in, serial out. I'm just giving data here serially, and data comes out here serially. Serial means it's one after another. That's how data comes out. And data comes out as and when you apply the clock. Now, clock is very important because that will synchronize other flip-flops also. What is synchronizing? When the rising edge comes here, rising edge comes to all the flip-flops. Okay, and all flip-flops will change its state. Okay, depending upon whatever the present state they have and present input, whatever is coming. We all know that, right? How flip-flop changes its state? Just now we discussed. The flip-flop, how it changes its state. It sees the present input and present state where it is, and it changes, goes to the next state. Look at the truth table written there, state table. It sees the input what you apply and present state and changes the next state. Here for 0, 0 condition, irrespective of the present state, it moves to the next state as 0, 0. Same thing here, 1, 1. Regardless of the present state, it moves to the what? 1. The data input is copied here. Okay. Simple way we can show that like this. This is moved to the next. This is ignored. Same way here also. This is moved to the next state. This is ignored. This is ignored. That's what D flip-flop will do. Just opposite the T flip-flop will do. Okay. And all are positive edge triggered D flip-flop. You may also ask a question why this is positive edge trigger. Why we always use positive edge trigger? Because in the entire the world, some part of the world uses negative edge triggered and some part of the world uses positive edge triggered. Especially in my opinion, seeing the US belt and others, they use negative edge triggered. Okay, if you look at any logic design, hardware design, they normally use here negative edge triggered. In negative edge triggered, you will see a bubble here. Okay, if I don't put any bubble here before the arrow mark here, just Okay, arrow mark here. That means it's a rising edge trigger. Okay. Why it is rising edge and falling edge? I am designing a shift register. Whenever the rising edge comes here, at that time I'm expecting the changes to happen here. Okay. If it is a falling edge, what will happen? When falling edge comes here, the state of the flip flop will change. That means this flip flop will ignore the rising edges if it is a falling edge. Okay, understand the difference? And it all depends on you, which kind of what kind of registers you are designing. You want rising edge, this is a flip flop registers are here. If you want falling edge, you can also do that. But internally you must consider. These are all symbols here. And it's just simply by putting a bubble, it doesn't make that it's a falling edge trigger, right? You must also design the flip flop inside this to be enabled with what? Falling edge, right? And you must design that and come to the symbolic representation. You should put a symbol over that. Blindly putting a bubble will not ensure that you have designed falling edge trigger flip flops here. Because so far what we have learned is rising edge trigger flip flop. Based on the same convention, I am using a symbolic representation. Nowhere I have spoken about negative edge trigger. And we have not discussed about negative edge trigger flip flop also. All flip flops what we have discussed is positive edge trigger only. Stick to any one particular notation. Don't confuse with both. Understand? But in industry you have a requirement of both. Sometimes they ask you to develop level triggers, sometimes positive edge trigger, sometimes negative edge trigger. You should be familiar with all kind of things. Okay, depending on circumstance. Any questions here? This is how data moves from the here to here. I showed with an example. I think that example will illustrate how data moves from one side to the next one. Yeah. Could you see this one? This slide shows you the how data moves. Suppose if I assume that 1011 is initial contents. It's not make nice. This is initial content is 101 is an assumption, and logic 0 is applied to the serial data. Now what happens when the rising edge comes? When the first rising edge comes, you can see the 0 has been inserted. This 101 will be moved here now. This one is last here. Okay, this one is last, and you have a data 0101. And if you can also take parallel outputs from all the flip flops, it is possible. Okay, but here I have showed serial output. You're only observing here and then last of the flip flop. In the second rising edge, what will happen? Again, you retain same 0 at the input. Therefore, the 0 along with this one more 0 will be inserted. And this 1 is last. This 0 moves here, this 1 moves here, and another 0 has been inserted. Okay, like this, at the fourth rising edge, you can see that all data have become 0 now. Okay, this one way you can see that. I showed rising edge here in the above. You can see here. This is another example I showed with rising edges. When rising edge comes, how data changes. Here I have inputted logic 1 here. You can see that here the 1 has been moved. Okay, the serially here to the outside. This is how the shift register works. And I think I have showed one more example. This is another example. We can use this as a circular shift register also. I'll show that here. One more. Yeah. A small change we did here. What we did here is the same as a block diagram. I've taken this output of this and given an input for this. By connecting a feedback here, you can see how the data moves here. If I assume that initial content is 1011 for this one, 1011. If the first rising edge comes here, you can see here I have made here as 1. I mean this data comes to the first input here. This data moves here and this data comes over here. It's 1101, 1110. This data moves here and this 1 comes over here. 0 comes over here. 0111, and lastly, after fourth positive edge, we'll have same data. Okay, this is called circular shift register. Mainly DSP applications use circular shift registers. When you perform operations like convolution, Fourier transforms, fast Fourier transforms, we mainly use these circular convolutions. I mean circular shift registers. Okay. Any questions about this? We have discussed about a couple of examples of shift registers, and what I would suggest you is now, before I move on to the bidirectional shift register, look at this one. This bidirectional shift register. These are two examples which I want to discuss before I move to the next topic. This, because in examination we ask you to write this circuit diagram, you can construct the logic diagram and ask you to give explanation for this. Okay, this is called as a parallel unidirectional shift registers. Just analyze here what will happen when you make load or shift 0. I'm just giving a task to you. A simple question is, you're applying some serial data over here. Okay, fine. I'm assuming here this load or shift is equal to 0. Can you just guess what happens for that? I myself have written there 0. You can see here 0 when you apply as an input. Okay, and this will be 1, right? It's inverted, it is 1, and 1 goes here. Okay, and this is parallel data which you can load. I've assumed some parallel data 1, 0, 1, 1. What is happening really is when you make this as a load or shift as a 0, the parallel data what you apply here, this is a parallel data 1, 0, 1, 1. Parallel data is labeled as IA, IB, IC, ID, and this complete data will get loaded onto the flip flops. Okay, when to load? You are supposed to load only when this load or shift signal when it is 0. When this is 0, because you can see there is a load, there is a bar in the load, right? Understand? When you want to load the data, you have to make this as 0, and when you want to shift the data, you have to make this as a 1. Understood that? So now I am making this as 0. That means this data 1, 0, 1, 1 will be loaded onto the shift register now. Wouldn't be loaded. The state will be occupied by the shift register. Here, look at here, 1 is there now. Since I made load as 0, load bar or shift as 0, the 0 becomes 1 here, and IA have made as a 1, and gate output, this is 1. What will be the output of an OR gate if one of the input is 1? Output is also 1, right? Irrespective of this, whether it is 0 or 1, the output becomes what? 1. That means I have loaded this with what? This flip flop with what? 1. Whenever the clock comes here, what will happen now? Rising edge comes. This 1 is there, it will move to the output of this flip flop. That's what happens, right? Look at what happens here. IB is made 0. I have not taken the uniform data. I have taken IA as 1, IB as 0, IC as 1, ID as 1. Random data I have taken. And if IB is 0, if I retain this as 0 itself, I'll assume that this load bar or shift as 0. Now see here, this becomes 0, this becomes 0 here. If one of the input of AND gate is 0, output is 0. And irrespective of this, this becomes, here it all depends on what data it is coming from the previous one. But presently I assume this is going to be 0, therefore input for the flip flop is 0. So what I want to say is now, when you make this signal as this line as 0, all this data will be loaded onto the flip flop, I mean shift register. And when you want to move the data from left side to the right side serially, you can do that by making this load bar or shift line as 1. It's very simple, right? Is it complex, this thing? Only thing is, for writing you may get confused the very first time, but if you practice it, it becomes easy for you. So this is basically a parallel link. You are applying data parallelly. Parallel data is IAIB, ICID, and you are getting unidirectional, the data are getting shifted. For doing that, you must apply here 1. Okay? This is simple circuit diagram. Any questions about this one? See, only two examples we are discussing. One is unidirectional, other one is bidirectional. This is unidirectional shift register. No need to worry about the design of this. What you need to do in examination is you must write this one and explain how it works. How to load the data, how to move the data. These operations you must learn it from this diagram. Any questions? Now look at this one. This is a bidirectional shift register. What is bidirectional? We can move to the left side. Left side is other side, right side. You can see here there is, you understand, various signals, notations, whatever used here, then come to the operation of this. There are multiplexers, there are flip-flops, all are rising gate trigger flip-flops. And look at what type of multiplexer we are using here. They are all 4:1 multiplex. Understand? So far, whatever I have explained, like serial in, parallel out, serial in, serial out, parallel in, parallel out, parallel in, serial out, all this can be done from this. That's why this is also called as universal shift register. What is the name given to this? It's a universal shift register. General purpose shift register. And this comes as in the form of an IC. You need not construct everything like this. This complete thing is available in the form of an IC. But for an IC, what you can see here is outside the IC, you will see this, you will see this, you will see all these signals. Okay? To load data parallelly, we have IA, IP, IC, ID. Okay? And to do multiple operations, like I told you, serial in, serial out, serial in, parallel out, for all those things, multiplexers are used. You may ask a question, why multiplexers are required here? Multiplexer is basically a combinational circuit. Because to have various options in the shift register. What are the various options? To move data serially, to move data parallelly out, and to accept data parallelly. Because here parallel data comes out here. QA, QB, QC, QD. Parallel outputs. Parallel inputs are here. Serial input is here. Serial output is here. And data can be moved from, like this also it can be moved. Okay? And it can be moved in the right side also. And data can be loaded. Look at here, serial input also. You can load data from this and move this side also. But you can load data here and move the right side also. All these options are possible. I suggest you to explore, because in the textbook it is, operation has been simplified by writing this truth table here. Okay? This itself, author says that it's an explanation for this entire logic diagram. What does it explain? Just look at this truth table. Can you see this one? Though it looks very small, for S1 and S0. What is S1 and S0 in the logic diagram? They are the selection lines, right? Look at it. These are S1 and S0. They are the mode control for the shift registers. When it is 0, 0, what happens? It is holding. It will not move data. It holds. Okay. When it is 0 and 1, it will do shift right. Check the operations by going to this. By making 0 and 1, look at what happens here now. S0 is, S1 is 0, S0 is 1. 0, 1. It will do shift right. 1, 0, it will do shift left. 1, 1, it will do parallel load. And now, as I told you that this complete, the logic diagram is available in the form of an IC like this, with all signals shown. Okay. For your reference, I have done actually. I think one explanation I have done. I will show you that. You can see the example here. This is what explanation I given for one operations. Like that, you can also try to understand other operations. How can you do with the diagram which I shown previously with the universal shift. When you make 0, 1, what happens to circuit diagram I shown here? I1 is connected to the F because that is through the multiplexer. And input element to the flip-flop is D, and that will keep on moving from one to the next one. You try to understand this by going through the logic diagram. And also other signals also I have tried my level best to explain here by making clear 0. Synchronously it will clear the entire shift registers. Okay. With that I will stop here. If you have any questions, I think this completes shift registers. Next class I will take with the counters. Okay, counters. Once I complete that, I think a few counter design I must do it in the class. Once I do that, I think this module also will be completed and be prepared for your test. We are thinking to postpone the test if everything works out. We'll see that because V2 has been postponed your last working day, right? I mean lateral entry last working day. Therefore, we are even planning to change the test dates.